Okay, so it is my pleasure to introduce today's speaker, Katia Piotrovskaya from the University College of London. And she will give a talk titled Base Extension Semantics, the Classical Chronicles. So please, Katia, the floor is yours.
Yeah, thank you, Antonio, for the introduction. So let's jump straight into what we're going to talk about today. Is it still working? Yeah. So first, it's great to talk to BTS community because I don't have to motivate BTS or explain what it is, as I expect all of you are familiar with it. But I don't expect familiarity with base extension semantics, which is a strand of BTS. I kind of expect that all of you have at least seen or heard of it before. That's why we first go through a quick recap of what it is. And you shouldn't be surprised I'm talking about base extension semantics because Antonio mentioned I'm from UCL and that's what we do here. Then we're going to discuss the approaches in BES, which is short for base extension semantics, that the approaches to give semantics to classical logics that have emerged in the past years. As you could have deduced, there's more than one. And that's why it's called the Classical Chronicles. And then we're going to wrap up with discussing, well, what do these approaches do? Are they all just like the same approach in disguise? What is to be done next? Yeah, and just wrap up the talk. Yeah, so let's do the recap. So we talk about base extension semantics. We always start with a conceivably infinite set of atoms. Think of them as atomic propositions that we just label as PQR, so lowercase Latin letters. Then we also have rules over these atoms, rules of 3 levels, the axioms, so level 0 rules, well, the usual level 1 rules, and the rules with hypothesis discharge. So the capital Latin letters would denote sets of atoms. And we have now the sets of the rules, which we call a base. So as an example here, we have a base B with the rules of P being an axiom and the rule that from P and Q we can deduce R and some other rules that we don't need to focus on right now. And let's say that we also have a base C, which has the exactly same rules as B, but it also has S as an axiom. In such a case, we say that C is an extension of B, meaning we have added some rules to B to get C. It could also be an empty set of rules, so B is its own extension. An important thing to note here is that, well, as in natural deduction, the rules are more like rule schemas, so that, let's say, and introduction would be phi, psi, and then you get phi and psi, then you could substitute any formula phi or psi there. Whereas here, when we say that P is an axiom, we mean that this specific atom is an axiom. So we can't, just because I have P as an axiom doesn't mean that we also have Q, R, S, or whichever atom you pick. So we can think of this basis as our set of atoms has some internal structure, namely these rules that, well, are said also to give meanings or definitions to those atoms. Well, let's stick with our base B. If we just had a set of rules, that would be very cool, but that wouldn't give us semantics straight ahead. So we want to have a relation that describes something related to B, which is called atomic derivability. So we have this turnstile indexed with the base B, and how this is read is B is derivable or provable in B, meaning that using just the rules of B, we can construct a proof of P. In this case, it's trivial, as you can see, P is already an axiom. Now, the left-hand side of the turnstile doesn't have to be empty. We can add some other atoms here. Important, this relation is on atoms only. So since we have the rule that from P and Q, we can deduce R, then it is indeed derivable that starting with P and Q as premises, we can conclude R. Now we also see that S does not have a proof in B. Well, imagine that S is never a conclusion of any rule. Then we just say that, well, S doesn't have a proof in B, therefore it's not derivable in B. all cool and clear, but well, we haven't seen any logical connectives coming up yet. And when we keep semantics to logic, it would be really nice to kind of have those. So our semantics is actually given in terms of the other relation called support, which builds on top of atomic derivability. So I wasn't just wasting your time for the past 3 minutes talking about something completely unrelated. It is very much related. And we'll talk about the support relation on the example of intuitionistic propositional logic given by Tor Sundquist in his 2015 paper. So in the base case, the support of atoms exactly coincides with atomic derivability. As you can see, support relation is also indexed with bases. Yeah, so that just says whichever atom is supported, it is if and only if it is derivable in the base. And then we inductively give the definition to the connectives, starting with implication. So we have that phi implies psi supported, if and only if phi supports psi. This is quite straightforward. We just push phi through the support relation in a sense. Then we have the conjunction, which is also quite intuitive, as you just split this into two conjuncts. We have that both phi and psi is supported if both of them are supported in the base. Then now is the complicated one. This is long. So now for phi or psi is supported, the clause for this is not given in terms of the introduction rule. So it doesn't hold that whenever this is supported, then phi is supported or psi is supported. In fact, this is given in terms of, well, inspired by the natural reduction elimination rule for disjunction. And you can see that there is the index of the support changed into C. So I haven't written it here, not to make the slides bulky, but that implicitly quantifies over all extensions of B. And an atom P there also quantifies over all atoms P. So basically, as this should be read, is if we take any extension of B, which validates that phi supports some atom P and psi supports that atom P, then atom P on its own has to be supported. So it has to be derivable in that base for any atom P. So this should work for P, Q, R, whichever atom you give me. And as you can see, this is the only clause so far that uses base extensions, but it's called base extension semantic for a reason. And lastly, the clause for bottom is that bottom is explosive. So here I put the all P because there was space, and for emphasis that, okay, bottom holds whenever we have a derivation of every atom in the base. As already said, an explosive base. Yeah, so if you don't fully get support and all of this, that's fine. You just have to have some broad picture of what we do with this semantics. And this is the semantics for intuitionistic propositional logic. And intuitionistic is not in the title of this talk, so we kind of have to shift to classical. But just before doing so, we can notice that when base extension semantics is given to intuitionistic logics, some patterns arise. So, well, whichever intuitionistic logics you give it to. So for one, we utilize all three levels of rules in the base. So we saw the axioms, level 1 rules, and rules with hypothesis discharge. Also, we operate over atoms, also as discussed before. Support of atoms exactly coincides with atomic derivability. And rules and the semantic clauses are all single conclusion, which makes sense, because the semantics is constructive. That seems like to work fine for intuitionistic logics. Very nice, but well, we know classical logics are not very constructive. So what do we do with them? Well, in fact, these 4 points here are not just observations, but also a plan for this talk in disguise. So in the following set of slides, we're going to see how we can alter each point at a time, and that the tweaking of just this point gives us classicality. So for instance, the slide is coming just after this one. We change point 1, but 2, 3, and 4 stay as they are. And that's going to be the pattern for each slide. So we just change one of these points. Okay, cool. So let's just start with that. So point number one is that we have all three levels of rules in the base. Well, screw that. Now we have two levels. So that was proposed by Tor Sandquist in his PhD thesis in 2005 for classical propositional logic, actually also for first-order logic, but we focus on just the propositional part for this talk. And later also developed by David Mackinson in 2014. So which rules do we keep? We keep level 0 and level 1 rules. So we forbid hypothesis discharge, essentially. Well, why would that give us classicality? Well, idea is that the double negation elimination is forced when we don't have level 2 rules. So the next point is going to be a bit technical for people who have worked with base extension semantics before, but essentially the intuition or idea behind it is that when we demand that, well, this Q for all Q is the definition of bottom, as you remember, essentially if P kind of implying bottom implies that bottom holds, since we don't have level 2 rules which condition on derivations, we no longer can condition on the derivation not P implies bottom. So it forces our original P to hold in the base. If you don't fully get it, that's also fine. But yeah, point being that not P implying bottom forces P, since not P implying bottom, as you know, in the reduction absurdum rule, it is a hypothesis discharge rule, but we no longer condition on derivations. So this forces P to actually be derivable in the original base. Now, what David Mackinson also did is he introduced the notion of maxi-consistent bases. What does that mean? So it's the basis that such that for any formula phi, either phi or the negation of phi holds in that base. Well, what does this give us? This is closer to model theoretic semantics in spirit, since we have this duality of phi or not phi. And this also makes the meta language classical, since most, if not all, of his proofs are through contradiction. And well, for Tor, and his thesis even emphasizes that the meta language is kept constructive throughout, whereas here it is classical. But importantly, what makes the semantics classical is not, of course, the meta language, but still that we only have two levels of rules. All right, so that's the first approach. We're shifting to the next one, which is that the units that we operate over are atoms. Now we're changing that to literals, which has been done by Alex Georgiou and Ul Buzoku, actually this year, for classical propositional logic. What's the idea behind that is, well, so for each statement C, we can either assert C or deny it, which gives rise to, well, assertion and denial indexed by this little plus and minus. And these things exactly are literals. So essentially, instead of just having a set of atoms, we have a set of atoms and their negations. So everything gets split into like a positive and negative counterpart in a sense. That alone is not enough. What else happens is that the duality operator perp is introduced, which is essentially redefined negation and evaluation function, where the evaluation function just assigns 0 or 1 to a formula. So it's kind of like the truth value function, if you wish. So how is duality operator defined? This may look like a lot, it's really not. So it just shifts the polarity of your statement. If it was an assertion, it becomes denial and vice versa. The next two lines are just the Morgan laws. And the last line is that the negation of the implication is actually phi and not psi. So as you can see, because of this, this operation is not involutive syntactically. But what fixes everything is that the evaluation function is forced to, so when you assign a value to the phi perp for some phi, it reverses the value of the original phi. So if it was 0, it becomes 1 and vice versa. So even though this operation, the perp operation, is not involutive syntactically, it is essentially involutive semantically because it preserves the truth value. Essentially, why that works, as the authors claim, is that when we have phi perp, this can denote either a formula that we achieved via the inductive definition on the left. So if we say open some brackets, when we applied perp operation to it, we got phi perp. Or I feel like this is going to be a bit convoluted. Or phi perp can denote a psi such that psi perp is equal to phi. So let's unfold this. Essentially, what this implies is this. So if to the right-hand side where we say psi perp is equal to phi, we apply perp to both sides, we get that psi perp is equal to phi perp. But we also just said that phi perp denotes psi. So essentially, this gives us the equivalence of, well, not psi and psi. So once again, this approach forces double negation elimination, but not on the level of the rules, but rather in terms of the definition of the negation operator and the evaluation function, which helps, because this phi perp might not syntactically equal to psi, but it has the same truth value. So perhaps an important distinction is the previous approach, Tor-Sandquist's approach, is classical logic without bivalence, which is also the title of his paper, whereas here we see classical logic very much with bivalence. All right, so ready for approach number 3. Here we have that the support of atoms directly coincides with atomic derivability. And here we're gonna switch logic for a bit. It's not gonna be classical propositional logic. It's gonna be a fragment of linear logic. So it might look a bit scary, like this. I'm talking about Moll here just because this is where this approach has first appeared. Well, it's my work with my co-authors, Victor Boros-Nascimento and Elaine Pimentel. But I'm going to comment on how this relates to the classical propositional logic as well. So as you see here, we also see that the support relation is not only indexed with a base, but it also has a superscript now, L, which is a multiset of atoms. And normally in this case, this correspondence between support and atomic derivability would be that P is supported in the presence of L, as it is read, if and only if P is derivable from L. Whereas, as you can see here, our base clause for atoms is not exactly that, or rather not that at all. But, well, a lot of things are happening here. So first of all, instead of the atom on the right, we see the bottom symbol. I'm going to explain that in a bit. For now, just ignore it or believe it works. Essentially, what this says, if you also ignore the K, is that P is supported whenever P proving bottom implies that bottom is provable. So as you can see, this very much looks like semantic reduction ad absurdum. So essentially, we get that P, if and only if not P implies bottom, so not P. Importantly, P being derivable still implies that P is supported. So what happens here is that since support is well defined in terms of atomic derivability, so it's a relation that's like the next level of abstraction from atomic derivability, is that at that level of support, we equate the idea when P is derivable and when not P is derivable. So that this is essentially what gives classicality. Yeah, I hope that makes sense. And well, also with the contrast with the usual approach. So the usual approach demands that we have a proof of P, so essentially a proof that ends with P, whereas here we demand a proof that begins with P. So essentially, this can also be thought of as a P is like the only atom in the base that prevents it from being an explosive base. Yeah, so remarks as promised. Number one, we're not really putting the bottom as an illogical constant in a base. We're just fixing an atom. So The role of the bottom here is it's not explosive because it's not explosive in linear logic. It is some fixed atom. So we could have chosen R, for example, and then we just always have R there. But we just chose to name it bottom because that would be the semantic interpretation of the logical constant. But we don't actually have the constant in the base. It's still just some fixed atom. Another point being, so as you saw in the support for intuitionistic propositional logic, the disjunction, the clause for disjunction demands a support of every atom. Like I was telling you that, okay, so if phi supports P and psi supports P, then P has to be supported, and that has to hold for each atom. So essentially, it's like we demand a proof of, well, countably infinite set of atoms, so that should hold for every atom. Whereas here, we demand, well, the clause demands a proof of just a single atom, the atom that we fixed and named bottom. Remark number 3 is that actually here, support is no longer a conservative extension of atomic derivability. What it means is that if we restrict our language at the level of the support relation to just the atoms, more atoms are supported than derivable, which means it's not a conservative extension. Which makes sense because, as I just said, the support kind of, at the support level, we equate the derivation of P and the derivation of not P. But if someone thinks that's very uncool, that the relation is not conservative, a conservative extension, we could also add this definition in terms of kind of semantic reduction absurdum into atomic derivability. And then this would be, the support would be a conservative extension. This is really a matter of choice and taste. And I think it looks quite neat when it's done at the support level because it gives this, well, like equating like at this level rather than at atomic derivability. But yeah, I mean, it's really up to other people if someone wants to continue this line of work. And I haven't shown the support clauses yet. So this might look a bit technical because it's linear logic. I'm not really expecting familiarity with linear logic. So we're going to go through that relatively quickly. And that's not the important part of the talk. The important part is here, as you can see for tensor on the right, once again, we demand just the support of bottom. So not like P for all P. Then another maybe important point is that the implication clause is no longer like simple. So it's no longer defined through just shifting phi to the left of the support relation, but instead it is based off the implication elimination clause, like the full one, where you have the phi and psi implying something, and then that thing is derivable. This is what we have here. And bar is really here just for people who have seen linear logic before. And since before this work, there was already semantics for intuitionistic linear logic given by Bulbuzaku. Well, the implication clause is different there, but par is not considered because it's not considered intuitionistic, but we also give a clause for par. So yeah, if you want to, if you're very like, oh, I don't like linear logic, or this is too complicated, for classical propositional logic, the same would hold, but instead of bottom being a constant, you would just use the clause for bottom, which is explosive. The reason we don't do it here is because bottom is not explosive in linear logic, 0 is. But if you apply the same restriction, so we apply the restriction to disjunction in intuitionistic propositional logic, that clause, so we just demand the support of bottom, and then we define the add clause in such a way, then it still gives us classical logic. The reason I talked about null is just because the idea originated from that paper. All right, very nice. So the next thing, like the final point, but not the final slide, is that in intuitionistic logics we have that rules and semantic clauses are all single conclusion. So screw that, we're entering the realm of multi-conclusion. Yeah, so first we're going to talk about, well, Tor Sandquist's PhD thesis again. Once again, just about the classical propositional logic fragment, not the first order logic fragment. So what's the idea there? How does it differ from point number 1, where only 2 levels of rules are kept in the base? Well, now, actually, instead of all rules having a single conclusion, we allow for multiple conclusion, and those are called the disjunctive rules. So there can be like as many as 0 conclusions. So essentially, the general shape of the rule looks like this. So we have n premises, so P1 through Pn, and m conclusions, Q1 through Qm. Now, how's that rule applied? The following way. So if we have P1 through Pn, and we see that from each like Qi, by discharging Qi, we get R, but it has to be the same R for each Qi, then we get the R. Essentially, this is like a generalized disjunction elimination. So in disjunction elimination, you would have like phi or psi on the left, and then you have that if from phi you have R, and from psi you have R, then you can conclude R. So the idea here is like this, but well, for more atoms, essentially. Now, one special case is the rule with empty conclusion and with n premises. Which kind of resembles X falso, but in this case, Tor calls it X P1 through Pn quadlibet. And this is what this basically says is that from P1 through Pn, we can conclude any atom. So this is also explosive. So this kind of behaviorally equivalent to bottom, essentially. Well, why is this classical? Once again, for the same reason as not P implies P, and that is forced. I was saying in the slides when we had point 1 that it is forced because we don't have rules with hypothesis discharge. And you may now tell me, well, Katya, now we have rules with hypothesis discharge. Does the reasoning break? It doesn't break, since we have a very specific shape of rules with hypothesis discharge. So you may think of it as we have level 2 rules now, but only when they look like this, only when they look like a generalized disjunctive rule. So for not P, not forcing P, we would need to have a rule that essentially looks like a bit like reduction ad absurdum, where we discharge not P and we get like a bottom, for example. But such shape of rules is still not allowed in the base. So the double negation elimination is still forced. If we have time at the end, I may also comment on, well, why is this approach needed when the approach from point 1 already exists? Why more rules have to be in the base and why this should be considered? I think I'll leave it to the end of the talk. Another approach would be this. So essentially, basic extension semantics is, kind of, as you see, the shape of the rules, all of that is defined in natural deduction style. So what happens now is that we shift perspective to sequent calculus, and we try to define both the rules in the base and the clauses of the support relation inspired by, sequent calculi. And that's also recent work with my co-authors, Victor and Elaine, for classical propositional logic. So what happens here, we have the following shapes of rules in the base. So now, there are only 2 types of rules because sequent calculi already operate over derivations in a sense. So we have axioms. Here, LK, PQ, so all these letters are sets of atoms. So as you can see, this is no longer a single conclusion because from some set of atoms L, we can conclude some set of atoms K. And this entire thing could be an axiom. And same on the right. So if we have, we already have some premises, we can have a conclusion. And now we denote the derivation as the sequent arrow, so quite standard. Now, what about atomic derivability? It stays more or less the same. So if P is an atom, then of course we would want P to derive P in a base, which makes sense. But now we also allow for weakening. So here M and N are any sets of atoms. So that essentially means the first line is that, okay, if P always proves P, that makes sense, but you can also weaken on the left or on the right with any set of atoms. Similarly, if L implies K is an axiom and that rule is in the base, then we have that L proves K, makes sense, plus the weakening on the left and on the right. I haven't written down the durability definition for a rule like which is not axiom shape, because that's going to be super long. But it is defined as you would expect it to be defined. If we have a derivations of every premise, then we have a derivation of the conclusion. And once again, weakening is allowed. That's very cool, probably also a bit technical. But what of the support clauses? Well, here we are. It's all of them at once, but please do not feel overwhelmed, because I will explain each of them. So first thing we can notice is, once again, the support of atoms directly coincides with atomic derivability. That's to comment on my point done like at the very beginning of the talk, where I said we tweak only like one of the 4 points at a time. So here we don't touch the add clause. Now the big L stands for the set of atoms. So here it's not only the rules in the base that are multi-conclusion, but also the clauses of the support relation, which wasn't the case for semantics, for example. Now the AND clause is exactly the same as before. So if phi and psi is supported, then we want phi to be supported and psi to be supported. But now you see that it's not just phi and psi, right? Because it's multi-conclusion. So we also have some other formulas, gamma. So formulas that are, well, not necessarily atomic are going to be denoted by Greek letters here. So big gamma means some set of formulas. And you see here, it's given in an additive presentation. So if one phi and psi comma gamma to be supported, that, well, we split phi and psi, but we keep gamma in both of them. That's fine, because we're dealing with CPL and contraction weakening are admissible, so that doesn't break anything. Now for the disjunction of phi or psi, it is defined as, well, we just kind of put a comma between them. So we just have phi, comma, psi, comma, gamma on the right, which makes sense because in a, well, a support relation, when we have a comma on the left, that means that is read as AND. So once we switch into the multi-conclusion setting, the comma on the right just naturally reads as OR. That is why the disjunction is essentially just a comma on the right. Now, implication is what you would expect it to be, as we've seen before. We just push the phi through the support relation to the left. Another interesting clause here is bottom clause, because we're saying that like bottom or gamma is supported if and only if gamma is supported. So if we read this from right to left, we see that we can weaken on the right with bottom, which isn't problematic. But maybe left to right reads a bit weird, just that we can, well, erase bottom. Well, let's see if that's actually problematic. Well, what happens? Well, maybe if you're very sharp, you'll be like, oh, but what happens when gamma is an empty set? Wouldn't that mean that bottom is supported whenever empty set is supported? And this would normally be read in base extension semantics as nothing is supported. And we know that's not true, because theorems of the system like P implies P are always supported. So is this weird? Does this lead to bottom never being supported? And if so, we face the same problem as was discussed in the paper by Thomas Piecha, Wagner de Camposenz, and Pierre Schroederheister, the failure of completeness in proof-theoretic semantics, which would force the not P to hold for every atom P. Is this, did we break this semantics? Actually, we didn't break it. Since we shifted to this sequent calculus perspective, what this is read as is not that nothing is supported, but rather that we have a rule that empty set implies empty set, and this is an axiom in the base, which is a perfectly fine sequent. It's a sequent that's never valid, of course, but since this is a definition of bottom, this makes sense. Both of these are falsity. And importantly, we still preserve the explosive nature of bottom, since bottom still implies that everything is supported, or anything is supported, since we allow for weakening. And if we essentially just have that bottom implies an empty, well, the support of an empty set, we can weaken with anything on the right. So delta here is for all sets, essentially. And yeah, so bottom still keeps its explosive nature. What's also interesting and different here is that normally, since bottom is defined as explosion, it demands the proof of every atom in the base, whereas here we demand just a single axiom in the base for bottom to be supported. So essentially, explosion here doesn't come from definition, but from a consequence of definition, which is pretty neat. Another nice thing about this specific semantics is that if we look at the sequent calculus for classical propositional logic, all of these clauses are defined based on the right introduction rules. So as I think in every base extension semantics talks, people quote Gensen. I also now, the time has come for me to do that as well, since, well, connectives are defined by our introduction rules. Finally, we have them also given in the support as through right introduction rules. Yay, fantastic. Yeah, that's it with point 4. But now, well, what's going on? I've been telling you about all of these different approaches. How do they tie together? Why, like, I talked about, okay, how does each one of them achieve classicality, but let's just have like a single picture. So essentially, as you might have noticed me saying over and over again, double negation elimination. So if we add this to intuitionistic logics, we get classical logic. And we notice that 3 of the 4 discussed approaches indeed do that. So either by the shape of the rules of the base, so that forces double negation elimination, or by a special function that defines negation plus evaluation functions that essentially equates the doubly negated formula with that formula in terms of truth values, or the add clause, which we've seen, which is literally written as reductio ad absurdum. And all of this boil down to not phi and plus phi, but these happen at a different level of granularity. So shape of the rules, that happens at the level of the base, nothing else is touched. For Alex Hanul's approach, we have this redefined negation, and of course, now that would, in order for that to also work on the atoms, we need to have atoms and their counterparts. So it's happening at the level of what we operate over, and now we have to operate over literals. And as just discussed, the add clause in the Moll paper, it happens at the level of support, since support is like this abstraction layer, which makes P, probability of P and probability of not P coincide. That's very cool, but I haven't talked about the sequent calculus approach here yet. Well, that's because what that approach forces is actually the excluded middle, so that not phi or phi holds in every base. And why does this work? It's because of the how the implication clause is defined. So if you recall all those clauses that are defined in terms of the right introduction rules of sequent calculi, if you just remove implication, and of course, multi-conclusion sequent calculi exists for intuitionistic logics, those can as well be intuitionistic. So say disjunction isn't problematic because that's also the right rule for disjunction and multi-conclusion intuitionistic sequent calculus. But what really makes it classical here is the multi-conclusion of the implication clause. Since if I just go back real quick, yeah, here, essentially, if we go left to right, that's fine. We just push the phi through the support relation. But if we go right to left, we have phi on the left, that's fine, but we have a set of formulas on the right. We have essentially a disjunct of formulas. So this clause allows us to pick any formula on the right to be a conclusion of the implication. And this is classical behavior. And this is exactly why excluded middle holds, because, well, not phi is defined as phi implying bottom. And this holds because you can choose your conclusion of implication on the right, and you can choose it to be bottom, so that you get phi implies bottom. Yeah, and once again, this is done at the level of the support relation, because now the support is defined to be multi-conclusion. Another thing to notice here is, at least as far as I understand, in the original, like in the 3 approaches on the top, it's the definitions, or like how these approaches are defined, that forces the double negation elimination. So it essentially comes first. And if one wants to prove that exclude middle holds, which of course it does because these are semantics for classical logics, then one has to use the fact that double negation elimination holds in order to prove the validity of exclude middle. So essentially, the double negation elimination comes first. Whereas in the sequent approach, it's really the exclude middle that comes first. And in order, in this case, to prove that not phi implies phi, one has to already know that not phi or phi hold in every base. So they are like dual, the top three approaches and the approach on the bottom are in a sense dual to one another as to which classical rule they arises from the definitions itself of the approach and which one is already provable using the other. Yes, so as you can see, there are these methods share similarities. They also have their differences. So what? I've been talking for how long? Already 40 minutes to you about all of that, and a natural question to ask, well, so what's the point? What's the take? Is there something super cool we're going to learn from all of this? Is one approach significantly cooler than the others? What like, should we do more of this? And well, the short answer is I don't know. The longer answer is different. So we can start analyzing these approaches, and maybe the first question that comes to mind when we see a list of things is, oh, which method is better? Well, you see better here is in quotation marks because, well, it's hard to find an objective way to define goodness of either of these approaches. So say one approach can be more philosophically motivated. Another approach could be applicable to a greater number of logics. A third approach could be easier to understand when one just enters the field of proof-theoretic semantics and perhaps easier to replicate. So it really, time will tell. For one example I can think of is that this sequent calculus approach, perhaps adapting this paradigm would allow us to give basic extension semantics to logics that don't have natural deduction systems. That's kind of like a future work or ideas we currently have. Or perhaps, well, since most of these approaches were given for propositional logic, are all of them capable of being extended to classical first-order logics? Maybe for some of them, it's easier or more natural to do so than the others. But this is all still to be done. And brings me to my next point is that, well, proof-theoretic semantics and especially basic extension semantics is still quite a young field. So it makes sense why these different approaches arose during this time. And I believe at this stage, it's great to explore new things or new methods of doing old things. So as the time passes, perhaps one approach will become the approach, or maybe it's going to be a number of them. But we'll only know once we collectively do more PTS and BES. And then brings me to my next point. Well, that said, should we continue to investigate even more ways to achieve classicality in basic extension semantics? Probably not. Not to discourage anyone. I'm not saying we shouldn't work with classical logics. On the contrary, so it would be nice to extend one or many of these approaches to first-order logic. So it's already been done by Tor in his thesis, for example, but that's for his approach. But my point being is that classicality isn't the only interesting thing about logics, and we already have this 4 or even perhaps 5 approaches. So maybe we should focus on other things, since all this talk about BES being a young field. I believe we should go in breadth rather than in depth. We should maybe investigate more the idea behind basic extension semantics or what else it could be applied to. For instance, since there are connections between intuitionistic logics and Heyting algebra and Heyting arithmetic, maybe we should check out how basic extension semantics applies to those. Or if I think about, say, labeled calculi for model logics, they are kind of based off Kripke semantics. if you look at them, maybe there could exist label calculate based off proof-theoretic semantics. So there are a lot of things to explore, and perhaps most of them have not been answered yet. And since the classicality question has already been answered in 4 or 5 different ways, maybe we should just kind of prioritize other things. Which brings me to, should we explore base extension semantic otherwise? Surely, yes, of course we should, for all the reasons I've just listed above. And well, not just base extension semantics, but proof-theoretic semantics as a field. Yeah, that's actually it from me for today. Thank you all for your attention. And I have the bibliography on the next slide with these little circles on the right denoting which point each paper corresponds to. And now this is really it. Thank you for your attention.